Hello.
Hello, sir. Good morning.
Harry. Good morning. All right. Hi. Hello. All right. Well, welcome. So I guess, Lalith, you had something you wanted to present?
Yes, sir. So just give me a second. I'll share the screen a moment.
All right.
Oh.
Hi, Harry.
So is my screen visible?
Yes. Yes.
So yeah. So this is basically a survey paper which gives us a brief introduction about and it gives in-depth analysis of various hypergraph neural networks that were done till 2024. So it was published in like a very good conference. So this is probably the tier 1 conference in like publishing like graph related works. So this is ACM KDD. It was published 2024. And so we'll go detail into that, and so we'll see like how these can be helpful for our specific data and all. So I've made a separate slides also which could detail a little bit about like how these are be useful for us, and I have mentioned like the pros and cons related to how it can be like a pro for us, pro con for us, and for our specific data. And I have some a glimpse of visualizations which can explain a little bit of hypergraph, this how can we model the higher order interactions and all. So let's go first understand. So the abstract. So higher order interactions are ubiquitous in real world complex systems and applications. So investigation of deep learning for higher order interactions become like a valuable agenda for data mining and machine learning communities. And as networks of higher order interactions are expressed mathematically as hypergraphs, and like hypergraph neural networks have emerged like a powerful tool to understand representation learning on hypergraphs. So given this trend, they have presented the first survey for like hypergraph neural network with an in-depth step-by-step guide. So here first what they try to do is they break up the existing hypergraph into 4 design components. So how do they design like input features, next input structures, then message passing mechanisms, and how do we train these training strategies. So, and also they examine how these hypergraph neural networks addresses and learns different higher order interactions. So, and also they give a small overview of related applications and recommendations for like medical science, bioinformatics, time series analysis, computer vision and all. So this is broadly a detailed survey of like how hypergraph input structures, input features, message packing mechanisms, and also how do we train these neural networks. So this is basically all about it. So yeah, so let's go into the introduction part. So here the higher order interactions are like pervasive in real world complex systems and applications. These relations describe multi-way or group-wise interactions. So here we call our, the higher order interactions that may happen in our C. elegans as anastomoses, right? I mean, I may be wrong, but it's more like that. So these anastomoses can be seen and, exploited using these hypergraph neural networks. And from the physical system and microbial communities and brain functions. So with specific to that brain functions, we consider the functional connectivity matrices or the structural connectivity matrices and build the graphs upon it. Like instead of traditional graphs, we apply hypergraphs to understand higher order interactions among distinguished parts of the brain. So that's one way of doing it. So when I worked with Mehul, we actually published a work into this space. So how these hypergraphs actually improve the performance in brain functionality for like autism spectrum and all. So and social networks. which is commonly seen, like the citations and all, and higher order interactions in like Facebook, the Twitter, the Pinterest and all. So yeah, the higher order interactions reveal several structural patterns that we can see unobserved in like pairwise counterparts, because there is no it's limited with the direct connections. But whereas here we can have like a grouped connection called like hyperedge among all these things. So we can have more informed dynamics. So for example, they have been shown to correlate with synchronization physical system, bacteria invasion, inhibition, and microbial communities, cortical dynamics in the brain, and contagion in the social network. So these are the various applications that can be seen. And also we can apply to our thing which we are working on, which is C. elegans, embryogenesis. So the hypergraph mathematically express the higher order networks or higher order interactions, where the nodes and the hyperedges respectively represent the entities of the higher order interactions. So we'll go detail into mathematics of how these are represented in the later sections. But right now we'll just see the basics, like what existing literature have done. So instead of having a straight two-node edge-to-edge pairwise graphs, hyperedge can actually connect any number of nodes, offering hypergraphs as an advantage in the descriptive power. For instance, we can see in the figure 1, where here we have like co-author publication. Instead of having like a dyadic connection between these authors, so we can have a nice hypergraph which can give a more stronger intuition rather than a simple dyadic connections. And yes, so next we'll see that hypergraphs are extensively utilized, and the demand grew, and make predictions on them, estimate hypernode properties, or identify missing hyperedges. Hypergraph neural network have shown the promise in solving such problems. For example, it has shown like significant application, including missing metabolic reactions and brain classification, traffic forecasting, production recommendation, and more. So before delving deep into these various things, so they decided to separate the hypergraph neural networks into like 3 main components. First is encoding, the training, and the application part. So the encoding purely focuses on how do the hypergraph neural network effectively capture these higher order interaction. And next, in the training, how do encoded higher order interaction. So these are like specific higher order interactions that they have fixed with. And now what are the training objectives that they wanted to plug in to get the desired outcome. So how are they doing that? So here they have given how do they model the higher order interactions. So this can be a nice intuition taxonomy they have provided. So here we can see that the external information can be shared like a feature or a label, and or one can take a structural information or an identity information in order to encode the input features. So that's one way of doing. And how do we design the input structure? One, we can use the reductive transformation, which may sometimes they are once we model the hypergraph into the space, sometimes you can't retrieve it back. So these are reductive. So non-reductive are like star, line, and tensor, and these are like clique and adaptive. So we'll go today. So I'll today discuss about like how do we encode the input features and how do we encode the input structure. So today's agenda would be discussing very detailed into these 2 specific topics. So next, if time permits, I'll in the next week I'll detail about like different message passing mechanisms, and then how can we train in order to extract the best messages and able to model these hypergraphs and understand these pairwise interactions. What could be a best objective to do that? So yeah, so for today's agenda we'll discuss about like input features, this red and the yellow component. So yeah, so preliminaries, these are the details of like this how do we represent. So here as we can see, so G is the hypergraph we said. So V here is the set of nodes, and E is not a dyadic connection but a hyperedge. So instead of an adjacency matrix, we here have an incidence matrix where it has like a 0, 1 components, whether there is a hyper-edge connection or not. And the shape of it is like V times C. So this is the cardinality of the node and the cardinality of edges, the shapes. So X is the input feature or the node feature that each and every node carries, and Y is the hyper-edge feature. So what does the hyper-edge carries the information? So that is also one of the important thing. So here PL is basically embedding of the node, and QL is basically hyper-edges at each layer and how are they incident. So this we're gonna discuss later on. So today's focus could be like till here, and we'll see like and N is basically the incident hyper-edge of the node Vi. So this is IN represents N by N identity matrix, so which has all the diagonal values 1 and remaining upper triangle and lower triangle element 0. So this is the indicator function. So indicator function says that if a specified condition exists, it's 1, else it's 0. So if the condition pass, it says true, then it's 1, it's not, either case 0. So here is the matrix of ith row and I, jth entry of the matrix M. Sigma is a sigmoid function or nonlinear activation, sigmoid or softmax or ReLU. So yeah, so how do they design this? Before designing the encoder design guidance, we have 2 steps. So as we have seen that step first would be, how do we design our input feature? How do we design our input structure? So here I have detailed today's topic of discussion. So maybe I'll show it on the slide and some from the paper. So design features to reflect region of interest. That is first. The second is design. How do we transform these features? That could become under like deductive transformations and non-deductive transformations. So here are the external features or the labels. So what are the external features or the labels? So here we extract features that come from external sources, such as timestamped events, text fields, which are not available in the hypergraph. So that we are trying to embed into the hypergraph. So those are called as external features. Suppose we have text or images or some, and we want to encode that information inside the node. So that is called as external features or the label. So how do we integrate that? So we concatenate these features, external features or labels, with the hypergraph's node or hyperedge representations. So one can incorporate inside a node, or we can incorporate as a hyperedge, so that these features are not directly assigned, but these are assigned based on the the kind of relationship that they have. Suppose we cannot directly put a given. Suppose we are trying to understand interaction between 3 images. Suppose say we cannot embed the entire image information inside the node. So no, for the node feature, whereas we can have like a short representations of the image, and we can encode the information about that the feature inside that node. Instead of encoding the image, we can encode the feature of that image. So that's how this external feature or label thing works. So what is the pro? What is the advantage of doing this thing? So it provides a complementary context by that's not captured by graph, because graph do not really have the information of the image encoding characteristics. So we directly encode the information from the image, saying that okay, these set of features are important for the interaction. So it interacts properly based on that information. So that's one of the advantage. So it enhances the model ability to learn from the specific cues that we have already curated and designed in that space. So temporal features can help track of time-based changes in the interaction. So so when we are trying to design a temporal, so say that, so we start from like embryogenesis of the first timestamp and second timestamp, and it goes on. So the interactions that we are trying to understand, so we can encode it in a certain fashion that we wanted to, that we desire. So that can be done doing that external feature or the labels. The disadvantages can be seen, or the cons can be seen, like so there may be noisy, sometimes incomplete or inconsistent if the external data is not well maintained. So if the if we haven't bought the correct representations that associate with the two neighborhoods or the two nodes, or we are trying to model the interaction, then it generally fails. So the pre-processing step requires like a little we have to ensure that we do a correct line of pre-processing instead of just focus on just dumping up the data. Or sometimes the external information might not directly indicate the higher order interaction. Suppose we are trying to find out relationship between three images where these three are do not even have a proper higher order interaction. So then this becomes like a not so useful thing to do. So there may be a misalignment, and we have to model it properly with careful when we are trying to model any certain like embryogenesis for C. elegans, without having a proper mathematical rigor of how do these things work, and we give in a certain fashion, they might not work. So there can be a misalignment with the patterns. So this can be seen. So that's one. So then we have the structural features. So yeah. So that's the main idea of like external features or labels. There are some of the papers that they have cited, like bag of word vectors, where they have a large corpus of data. Instead of feeding that large corpus of data, they have given this to like a bag of word vectors, and these vectors are fed into that each and every node. So there are like several other papers which have used this type of work, and they have mentioned that this can be done in several. There are several methods which we have done, and they have incorporated things in such a way. So, and next we jump into the structural features. So, yes, structural features. Yeah. So in the structural features, so we derive directly from the hypergraph topology. So if you have a correct topology, so we extract the structural features from the topology itself. For example, when we are trying to compute, when we are trying to understand the structural features of a, evolving a graph or evolving, the C. elegans. Suppose we believe that, from the parent and the child actually grows from like, AB cell to ABP and all. So this lineage graph, when we are trying to design a structural feature, then we can say that the interaction that happens from like the parent cell to the two child. So we can design this as like a structural feature, saying that this is the parent to child interaction. We can design an hyper edge on top of that. So this hyper edge that we use on top of these three children, like two children and one parent, could be seen like a structural features, because we extracted the same from the topology. And when we are trying to learn the characteristics, suppose what is the similarity, how are these related based on the distances? So that we can encode based on the structural features. So this is one way of doing it. So when we capture the inherent relationship patterns and we can capture higher order connectivity that defines in the, the higher order interactions. So based on the given structure, we can able to, identify the things properly based on the given structure itself. So here we do not specifically need not encode certain additional details into it, but we can understand the things that, which actually interacts with what and all. So who interacts with whom. So this can be nicely seen in this graphs. So what can be particularly robust in settings where external features are absent or sparse. So this can be very advantageous in that scenario. And where it can be disadvantageous, so the extraction and computation of structural features can be little computationally expensive. And there needs like a little more data set, because in order to train such complexities, and so may require some parametric tuning in order to design these hypergraphs. That could be a little problem. That's not a big problem, but while when we have like a big corpus, we want to try to get some certainty, like structural features from like small motifs, then it becomes like a problem. So the possibility of information redundancy, if too many similar structures are there, then there is that. So if the structure, the motifs that we regularly see in that the hypergraphs that we design, that the problem comes is these can be repetitive in certain parts, and these repetitions can also get captured in this when we take the structural features. So that can be the second disadvantage. So what people have come up with is there is another thing called identity features. In identity features, what we have is we assign a unique identifier to each node. Suppose the lineage graph is the best example for this, because it's a unique identifier, because it starts from a parent, specified parent, and then it slowly evolves into like a child, and the child has like two, the child becomes a parent to other two children, and the graph grows accordingly. So this is one of the good way to do it. So what they do is, when these are specified accordingly, then the thing that can be seen is for the identity features, this the higher order the higher order interactions can be captured using a random vectors. So when we initialize using a random vector embeddings, then we do not specifically know, it's everything is unique, right? So we try to understand the higher order relationships between by assigning some random feature, random hypernodes, and then we learn the hyper edges. So we design a hyper edge, randomly we initialize it, and then learn based on the interactions that we see accordingly. So this is particularly seen in many of the cases. So what is the advantage of this is guarantees that each entity has its own unique representation, and which can be beneficially tasked for recommendation systems and all, and also for our task, which I have mentioned, and acts a fallback mechanism when external or structural signals are pretty much weak. So, and the disadvantages that we can see is by themselves, identity features do not capture relational or contextual nuances between the entities. So they do not, we cannot say that, okay, these can be a hyperedge that we can form between these, features. No, we can't do that. So we assign randomly, and we learn based on the interaction that happens. And next, this can have increase of overfitting if you have less amount of data. So basically, whatever the random higher order interactions that we're trying to design, they might not exactly fall into the space. They might not, there are some interactions that it fixes and it does not learn. So it generally, or either it has a certain pattern and it fixes it like that and it memorizes, but not, generalizes. So pure generalization can be seen in certain cases where, if we are using solely the identity information. So these are the different feature extraction mechanisms that we have seen, other than the dyadic connections between the simple GNNs. So now what they say is, we have how do we express hypergraph to reflect the higher order interactions? So how do we express them? So how do we have to construct an hypergraph in order to learn better features? So here there is a good example of the hypergraph. So this is one way of doing it, is clique expanded graph, and another is star expanded graph. So they divided this type of expressions into reductive transformations and also non-reductive transformations. So what in reductive transformations they do is, so let's go a little into reductive transformations. Yeah. So in reductive transformation, first is clique expansion. So what clique does is, so it tries to transform the hypergraph, that is at each hyperedge, into a complete graph with the clique. Okay, the connections that are being established with the nodes, with every pair of the nodes, it tries to form a clique. Based on that clique, this forms a this type of graph. Suppose let us take example here that could be very useful for us right now. So here we can see a hypergraph saying that 1, 2, 3, 4, 5. So these are the 5 nodes, and A is one hyperedge, B is hyperedge, C is a hyperedge. So A is having hyperedge between 1, 3, and 4. Node 1, 3, and 4. So hence we have an interaction between 1, 3 and 4. So this is a clique that we have formed. So this is 1 by 3, this is 2 by 3 and this is 1 by 3. Why this 3 and 4 has 2 by 3 instead of 1 by 3 is, so here this 3 and 4 shares the hyperedge between both A and B. So suppose it has a 1, 3 and 4 are saying that 1 to 3 is 1 by 3, 3 to 4 is 1 by 3 and 1 to 4 is 1 by 3. So it gives 1. So 1 by 3 plus 1 by 3 plus 1 by 3, 1. So in the similar fashion for the B, we get that. So but whereas this 3 and 4 shares a common 2 interactions from both the hyperedges. So that is A and B. So it gives the 3. So that this. So let's go understand how is this clique expansion done and all. So this computes edgewise weights between and factors such as node pair co-occurrence frequencies. So this how many times that? So as we have seen, 3 and 4 occurs twice, and so we give the node pair frequency as 2 by 3, and the normalization is done accordingly. The weight attempts to mitigate the distortion from the various complete cliques. So the weight is attempts to give a proper unification. Uniform distribution of the weights. It designs and which has like more number of co-occurrences. It has more weight. So what is the advantage of this? It allows direct use of established hypergraph for the spectral filters. And this is simple and well understood approach. But what is the main disadvantage is it loses some of the structural information about like exact hyperedge membership. So the higher order interactions, they might not exactly be the way the clique has constructed, because the hyperedge structure is replaced by pairwise connections again. So, and sometimes this might lead to redundant connectivity. So these are the main 2 disadvantages that we see. And also the expansions that we do, right? Using these approaches, they cannot be again transformed back. So, we cannot recover the hypergraph back once we construct back into this sometimes. So that is the main disadvantage. So adaptive expansion. So the change here is for the adaptive expansion, as we have seen in the clique expansion, we have decided some set of weights uniformly divided. Instead of defining certain uniform weights, we actually give selective weights or learnable weights, saying per se that there are certain interactions that are unnecessary, but we have added a node, so then we remove that, or there is a little more importance that we add to it. So instead of forming a full clique, they selectively add or weigh edges with a hypergraph based on full driven criteria, like it's distance based, node based, feature vectors and all. And also one can identify 2 anchor nodes per hyperedge based on the maximum feature difference, and one connects those anchors to the other nodes. Generally, this strategy helps to change the features or the representations or the interactions little bit and gives little priority to those who have like a good data characteristics. Suppose per se we say that we have the interaction between 2 networks, saying one network has like very limited information or missing information, then we simply discard based on the adaptive expansion. So this is one way of doing. So what it does is it mitigates the noise by avoiding unnecessary or redundant edges and tailors a proper, weighted, specific, more preserving higher order interaction nuances. This can be preserved. But disadvantage is it's very complex to implement because we do not specifically know what exactly to give a proper weight on top of that. And these distance measures are not very useful in the real world. So this is very potentially sensitive to very parametric settings and noise, and not really applicable on the real world data. So what now we are trying to understand is non-reductive transformation. One is star expansion. So here we see that this is one of the non-reductive expansion. We have seen the star expansion. Here, instead of forming a clique, what we do is we design A, B, C as 2 different entities, saying that these are 3 hypernodes, these hyperedges, which are connected to 1 and 4 and 3. So 1, 3 and 4, A is connected. So as the hyperedge is there, so here this has an interaction. Instead of forming, so instead of having a a clique type of representation. So these representations can be simply a bipartite graph where A act like a edges or the hyper edges. The nodes, the blue color ones acts like a hyper nodes or simply nodes. So this way we can actually encode the information into the, we can understand the, the better higher order relationships can be acquired using this bipartite approach. Oh, sorry. So yeah. Sorry. Yeah. So this fully preserves the original hypergraph information, and hyperedge can be recovered easily. Exactly. And it's a clear separation between nodes and hyperedges. It facilitates we can specify which kind of message passing that we can use so that it can give better outcomes. And the disadvantages of this is doubles the number of nodes and increases the complexity of the graph. So algorithms must be now handle the bipartite structure, and the adaptation mechanisms that we use for traditional graphs may not be exactly useful here. So we have to design our own way of training, these type of networks. So the another one is line expansion. So this converts each pair of nodes into, two distinguished nodes into a new graph. So this connects new nodes if they share the same original node or the hyperedge, or this distributes the information into a higher dimensional structure where the relationship among the pairs are explicitly encoded. So the main advantage of this line expansion is this maintains the exact membership of the nodes to hyperedges. This can capture more complex interaction and serve like node to hyperedge association, similar to that of star expansion. And this may result in very large amount of number of nodes, and thus it increases the computational cost. And sometimes the graph can be very sparse, the information that may not be useful, and it's quite difficult to interpret from this line expansion. So finally, this is like a tensor expansion. So we represent a given hypergraph into a higher order tensor. We call it K uniform hypergraphs or K order tensor, where each entry indicates the specific set of nodes form a hyperedge or not. So we have basically this tensor expansion is basically imparted into this PyTorch geometric and these other mechanisms where all the features are saved into a K tensor uniform hypergraph tensors, and these tensors multiply and give more distinguished higher order interactions. So there is no loss of information in this tensor expansion. The original hypergraph structure is well maintained, and it also allows multilinear algebraic techniques to analyze higher order interactions. So we use matrix multiplication, we use hard-math product to understand each hyperedge to multiple and nodes relationship. So we can use a simple matrix multiplication across tensors, and we can see how are these the distributed higher order interactions are spread. And so this is also computationally expensive and impractical for scaling the graphs, which is non-uniform and all. So these are the two different sections that I've covered for today. So if you have any doubts, then I'll be more than open, helpful to discuss.
Well, that's great. Thank you. So any questions or comments?
Yes, I've got one.
Yeah,
Lalith, did I hear you say that you could turn synticial relationships in a lineage tree into a hypergraph?
Sorry, I missed somewhere. I'm sorry.
Okay, if you take the nematode lineage tree.
Yes.
Okay? There's plenty of information that there are synticial cells
Yes.
in it. can you make a hypergraph representing these synticial relationships?
So what can we do is, initially we can start off with a random initiation of saying that, these are synticial relationships per se, and later on we can use our methods. We can learn slowly, adapting that, okay, may not be these, but these are synticial relationships that actually are. So we can do that, sir.
Okay, because I think Bradley and I have been discussing getting a synticial graph of a nematode, and perhaps a hypergraph approach would work.
Yeah. So, I mean, another question kind of related to that are these sort of reticulated. Well, I guess you have reticulating relationships in graphs by nature, but sometimes you have bidirectionality. Sometimes you have loops, things like that.
Right.
So it's learning those kind of relationships alongside the actual topologies. In other words, it's connected in a certain way, but we don't really know we kind of know from message passing what the flow might be, like what goes from where, what node to what other node. So it's learning that pattern as well as the topology.
Right.
Yeah, but I'm proposing that it would be very worthwhile to write a paper on hypergraphs as representations of synticial relationships in the lineage tree of C. elegans. Very explicit, and it would take mining literature. All I've found so far is people talking about up to 44 different synticial tissues, which is quite a bit. Okay. So making such a modified lineage tree would be quite worthwhile. I mean, Bradley and I have been talking about making a simple one with just one synticial tissue, but perhaps one could go for all 44 synticial tissues. Okay, and do it right and do it thoroughly, and I think it could have a major impact. Because the lineage tree is not the correct tree. As hollow as it may be. Okay.
Sir, can you give me a little more context about this synticial interactions? Little bit. I mean, really confused. Biologically, you can explain, then probably I can map into.
Yeah, I'm saying insofar as the data allows. Obviously, if you can't be sure, it becomes vague or you leave it out. But people are claiming 44 synticial tissues. Perhaps at least some of them, there's enough information so that we could make maybe a hypergraph of it.
Right.
Okay. And I think this could be very important in the development of the C. elegans embryo.
Right. Also, I wanted to show some kind of visualizations I tried on. So they may not actually be very much useful right now, but maybe later on. The reason why I've tried this, the visualization is I'm trying to understand where exactly I wanted to have like a higher order interaction. In order to do so, the visualization has become a little impediment to start off.
Okay, I did a quick search a minute ago, and I found that there are only 203 papers on synticial relationships in C. elegans.
I mean, yeah.
So amongst those might be some with data that we can actually use.
So what I was trying to understand here is, so I wanted to see like how in three-dimensional structure So how the parent. So here we have first timestamp. What we have done is so I wanted to see like this is the parent. It has split into like ABP and ABA, and here the another comes like these are from which the children are related. I mean like defined like a nodes here like round, and from which it has evolved. The parent is red color. This what I call is the square one. What I have done is this is for first time point. The next time point I've seen that. Okay. So what are the new set of things that were added? So I've given green color to them. So I'm trying to understand. So here it started with this So here it started with AB1 and then it expanded and slowly it expanded. So how are these relationships modeled? So in the three-dimensional, in a proper three-dimensional. So I have checked whether these locations are correct or not. And yes, they are. And so I'm able to see in a three-dimensional space that how are these cells, the parent has been divided into the two children. So, and then for the next time step, I did only for like, initial experiment sort of, because I wanted to see like how they split actually. So most of the time what happens is they randomly, evolve, and they, when I do the entire for all the time points, it gets cluttered. So I've just plotted it for like 3 time points, have seen like how they are moving. Now, based on proximities, based on the distances, so based on, this, so we can model the hypergraphs. Or say, suppose now this portion, so this E3, BA1, this portion, this all can be modeled using a hypergraph. I mean like hypernode, suppose. And these all can be node. We do not know the exact higher order relationships that we can model, but we can start off saying that, okay, these set of, things can be done. So this is the data that I have found from like the temporal data that I have found from like DevoGraph. So this can be done for all the time points, but it gets cluttered. So I just visualized for only few time points, and this is reproducible, and probably I can, can share the code.
Yeah, that's in a notebook, right? Yeah, please share that.
Yes, I'll.
Yeah.
So in the report, I haven't mentioned the 3-dimensional. I mentioned only the 2D, but my idea was like in the similar type. I mean, like these expansions happen in the embryogenesis happen with these expansion, and these are the lineage tree that it grows in this fashion. And now I wanted to model the relationships among this, not just the dyadic, but the using an hyper edge. So how do we do that? So that's why I was reading that paper, which could be an exact app to structure that we have to choose. Is it a structural features, or is it like the identity features, or we externally provide some certain set of features, or how do we design this transformation? Do we have to do it in a star graph, or do we have to do it in a tensor way? So I was starting off that initially. Next, we can go into the message passing mechanisms and see that what exactly can be put into this space, and we can go into much detail. So I think this was like a kind of, and this is the main advantage of this is we can see it, we can modify it, and we can zoom it, and we can play around with these visualizations. So where exactly it's been modeled, and we get all the coordinates, and is it a daughter node or a mother node, a parent node? We get the information about that.
Yeah.
So
I mean, the interesting thing. So could you bring that back up? I wanted to.
Yes.
So. Okay. So you see these on the left here, this 3-dimensional space with all of the cells. So the cells that you're marking are the nuclei of each cell, and then of course you have
right.
multiple generations, so that's the expansion part. And then, so
Yes.
a synticial cell would be like if you have an expansion and they kind of spread out, they're division events and spatially they spread out. Synticial expansion might be like where they divide to a point where the nuclei are in different spaces, but they're all sort of in one cell. So they reticulate in the sense that they're not different cells, but they still, there's still these independent nuclei which we're tracking. Because if you look in the lineage tree, you'll see that, like the way they represent it is it's a bifurcating tree. It goes down many generations, and then they treat every synticium as like a series of different cells that are terminally differentiated, meaning that they divide, they have this identity as a mature cell, and then that's the end of it. They don't talk about it anymore. I mean, they don't show like how, they don't, the lineage tree representation usually don't describe or don't make the distinction between like specific nuclei, like we have here, and cell bodies. So each of these nuclei are presumed to be an independent cell body, albeit like, different generations. So you have one cell body that becomes two cell bodies and two nuclei, and those kind of like have their own place. But then in the synticial case, you have all of these nuclei that are maybe distributed in space, but are now part of the same cell body that is like one single thing. And so you'll see that, you don't see that in the lineage tree. And it's, it's kind of interesting because if you take, I was actually playing around with this from the data for pharynx, and you can collect like all the cells that they mentioned for pharynx and kind of put them in a representation. It's kind of hard to represent it. I mean, you have they're not contiguous in the lineage tree, so they're different parts of the lineage tree. But ostensibly they'll be in a similar, or they'll be in sort of a, maybe like an arc along in a spatial location, like a set of spatial locations that might form an arc or some continuous feature. So, you might think, well, if I look at this lineage tree down here on the left, you have the red cells that are discontinuous, the green cells are discontinuous. You might actually have, like in the case of a synticium, all the green cells forming like a ridge in this space.
Right.
Along an arc. Or they could be discontinuous, but the cell body kind of snakes around and incorporates them.
Right.
And then, that would kind of be a hypernode.
Right. Yes, sir.
So I mean, that might be like a unique opportunity to like define a hypernode. Like if we know, that's kind of like the preprint that I put out.
Yes.
That was what was being described, was that you have these labels, but the labels are not just like just like linguistic. They're actually phenomenological. You have these like it's all the nuclei within a cell body, or all the nuclei of a certain cell type, like a neuron. We have those categories that are naturally in the biology, so we don't have to guess as to what the hypernodes contain. They contain things, but then how do you get to those things? Because you have this process of cell division and differentiation to get there. So I mean, in C. elegans, it's pretty deterministic. But in like other organisms, where you have regulative development, it's not. It's very different, and it's going to have different constituents in those systems.
So I mean, like technically, or so first we can say that these do belongs to a same hypernode, and then green all belongs to a same hypernode. Saying that this 1 and 2 are based on the connections, we can say that they have like an overlap, and the blue ones that we have here, so they do belong to the next 3 levels of hypernodes. So they evolve over the time, like these higher order interactions. So this is just an assumption, but so this can be modeled in that way, saying that, these three cells were actually have come up from the same parent. So they do share the similar, the cell body. Although the nuclei are like separated, but they have shared the cell body. So they might share the certain sets of biological features underlying, and so the evolution happens and have these set of connections. So we can, I think, modeling those could be a little interesting line.
Yeah, that sounds good. So that looks good. Also, those kind of visualizations, we're doing things like that. I think they're featured in one of the papers. I'll send you the paper that has them.
Okay.
They're not modeled in, well, they're kind of the same kind of, considering the graph from a 3D perspective like that.
Okay.
So we have, but like this, I mean, it's basically the same intuition. And we didn't, we were actually doing things like calculating angles in this space.
Oh.
So it's interesting.
Oh.
But yeah, I mean, we've been talking about like, so you have other types of features in those graphs. Like if you have a parent cell and two daughter cells, the cell division event that represents is where the nuclei, one nucleus becomes two.
Two.
There's the cell body that divides and the cells migrate. Then those cells have differentiated from the parent, but then you can calculate sort of an angle, phase angle between the two daughters.
Oh.
So the idea would be like you take that phase angle and you'd say, what is the similarity of the phase angle maybe between, within a sublineage, or like between the anterior and the posterior. It's just another parameter you can use to look at cell division and what it's doing, what's going on. You might have cells that migrate far away, you might have cells that don't migrate at all. You can describe that process. I mean, you can describe the distance between them, but you can also describe that phase angle. And, yeah.
So based on the three-dimensional coordinates, we can say that, from here it started here. So based on that, we can determine the phase angle. So we can that.
More than that, you can get the flow of cells over time.
Sorry?
You can get the flow of cells over time.
Yeah.
Where does the cell move?
Right.
And you can draw an arrow.
Right.
And, that gives you a kind of flow.
Right.
Okay. Bradley, do we have any flow diagrams for C. elegans?
I don't know. I think we had worked out some diagrams. I don't know if they're flow diagrams per se. I'll have to pull them up because I have some examples, but I don't
okay.
Think,
yeah, I mean, because in a sense, as the embryo grows, there's a flow of cells. And how do we visualize that flow?
Right.
You could, for example, every time you get a cell, it divides, and then then there's a later division. You could use the centroid of the second generation of cells, okay, to make an arrow.
Yeah.
Now, of course, that won't show you the divergence if they end up far apart. Okay, that's why I say it's a problem is how to represent this. But I think it's very interesting. These hypergraphs and perhaps flow graphs, etc., might give us new ways of looking at the development.
So you were suggesting there are like 200 papers that were present for this synticial nature of C. elegans you're trying to model. So
Yes,
can you say one of one of them interesting?
No, I can't send one. I can't. I'm having trouble downloading them for some stupid reason. I'll work on it later.
You can send the digital object identifier or the
I'll
link.
send you out 200 so you can skim over them. Okay, but I was trying to download them and it's not working for some reason. I think they're having trouble at the company that has them. Okay, so the literature is there. How much of it is more than qualitative, I don't know.
Mhm.
Okay, but I think it's time to move on and get away from what was it, Sultan? Who did the original?
Solston, yeah.
Sultan.
Yeah.
He did the original tree, but that was in the 1970s.
Yeah.
And, he did it by hand, and I think it's time to go beyond that, considering the claims of all these synticial cells.
Right.
Okay, time to understand what's actually happening, not what you have no Nobel Prize for.
Yeah, that's good. Soham, did you have anything to add? I mean, you turned your camera on.
I don't really have anything to add. Okay. Sir, also I wanted to mention that I haven't spent much time reviewing the reports. It could be good if I had little more time given to you. So that was really last minute. I should have mailed you at least a week earlier so that you could have reviewed and give me a good suggestion or feedback based on that. So did you look into it?
Yeah. I'll take a look at it. Or I'll be evaluating proposals. So yeah. Give me some time to get.
Yeah.
So, yeah. All right. So I guess that's it for this week.
Yes, sir.
Thank you, Lalith, for great presentation and discussion.
Okay.
All right. Thanks.
Okay, sir.
See you next week.
Thank you.
Bye.
Thank you. Bye.
All right. So some follow-up from today's meeting. I wanted to highlight two papers that maybe put some of the stuff we did today in context. So the first paper is this paper, Dynamic Morphoskeletons in Development. This is a paper I put into a lecture on Moyer morphogenesis, which is on the YouTube channel. This is by a number of authors from Harvard and the Kavli Institute. So this is where they're using flows, particularly Lagrangian coherent structures, which are mathematical tools to describe flows, to think about morphogenesis in developmental biology. So why don't we look at the abstract? Morphogenetic flows in developmental biology are characterized by the coordinated motion of thousands of cells that organize into tissues. So in a lot of organisms, you have these flows of cells as they're dividing, and they move through cell migration to different locations in the embryo. And those flows, we can characterize them. Sometimes, these are systems with many, many more cells than we see in C. elegans. And we can characterize those cells as sort of having a certain pattern of migration. So what we're interested in is looking at movement as a flow and then describing that in terms of hydrodynamics. And so, this is something that the tool that people use. They use a Lagrangian, and we use. We'll get into the mathematics later. So, naturally raising the question of how this collective organization arises, using only the kinematics of tissue deformation, which naturally integrates local and global mechanisms along the cell paths. So they basically use a differencing mechanism to look at the divergence of cells and their relative position. So they're using the kinematics in this hydrodynamic flow. We identify the dynamic morphoskeletons behind morphogenesis. So the way they define dynamic morphoskeletons is the evolving centerpieces of multicellular trajectory patterns. So you have these trajectories of these cells. They're basically going to be similar because they evolve in these flows, and you can characterize sort of the most common trajectories from this analysis. These features are model and parameter free, frame invariant, and robust to measurement errors, and can be computed from unfiltered cell velocity. So the kind of data we need for this is to have sort of an origin point and a set of points in time that change. So a cell will have sort of an initial location, and then for each cell that we're analyzing, and then those cells will move over time. And you take this trajectory, you can have the continuous case, you can have the discrete case, and you can calculate that trajectory from time 0 to time n. And so then we also want to look at the difference between, say, 2 or more cells and look at how those trajectories kind of converge. So this is a different type of tool than, say, like cell. It's actually maybe a level above cell tracking. Whereas in cell tracking, we get specific information for each cell, the location of its nucleus. In this case, we have that nucleus. We're tracking it over time, but we're looking at sort of the derivative of motion, and we're characterizing that in terms of a trajectory, and cells in terms of different cells and how their position relates to one another. We reveal the spatial attractors and repellers of the embryo by quantifying its Lagrangian information that is inaccessible to simple trajectory inspection. So this is where, again, we're using this derivative of just simply projecting out the positions and calculating out a line or a function. We could also use Eulerian methods that are local and typically frame dependent. So Eulerian methods don't give us the kind of temporal resolution across the embryo that we would like. Computing these dynamic morphoskeletons in wild type and mutant chick and fly embryos, we find that they capture the early footprint of non-morphogenetic features, reveal new ones, and quantitatively distinguish between different phenotypes. Figure 1 shows the dynamic morphoskeleton of what it looks like. So you have a cell in an embryo, and it can move in many different directions from its origin point. So it has an origin point, and it moves either outward in a number of directions, or it remains stable. So if it remains stable, we don't have to worry about it. If these particles move in a certain direction, then we want to track that position and the changes in its position over time. So in A, it kind of shows the context of this in an embryo. In B, it shows the cell velocity field, which is the area around the cell that conditions how far and fast a particle can be characterized by its nucleus. On the left, we have the Eulerian approach, and on the right, we have the Lagrangian approach. So in the Eulerian approach, we have the cell velocity field, and we have this clump of cells in the middle, and we can describe them. And we have this sort of point model, which is interesting, but the Lagrangian approach allows us to characterize cell position relative to the flow field. So you have more information as it evolves. So on the right, we have the Lagrangian coherent structures. So there are a number of methods that we can use for a Lagrangian coherent structure with memory. So the Lagrangian has a memory, as we can see on the left. The first measure is the FTLE measure, or the one that they're going to focus on in this paper. And this is the finite time Lyapunov exponent. So we can use a Lyapunov exponent to characterize the time evolution. And this is a finite equation for finite time. So it means that you go from t0 to tn, and you measure that many points, and you characterize the trajectory over those points. So the reason they're using the FTLE in this paper is because it's computationally simple. you have your integral, so you're integrating from t0 to tn, and within that interval, you're calculating the velocity and then changes in that velocity. So that's basically what you're getting. So it allows you to it gives you this Lagrangian flow map, which is given by this equation 1, which maps the initial positions of cells. And you could have, we're talking about cell nuclei here. We could also map the change in position of cell membranes or of cell bodies, if we can characterize a cell body, and do all of those things. Depends on our input data. So this shows sort of a conceptual view of the FTLE. So you can see in figure 2a, you have this origin point, which is x0, and you can see that x0 can evolve to a number of end states of xt, which have a range of values. So typically you have maybe the information for the initial point and then the next point, because it's a continuous measure. So we're characterizing it as a continuous measure, but we have discrete data. We have to sort of interpolate a lot of these points. So we go from our origin point x0 to different points of xt, and those different points of xt form this ridge. So we end up with this ridge of values that are described. We can describe that mathematically. We can also describe a ridge of values going from our origin points to another set of origin points. So we can go forward in time or backward in time. We can go from origin to destination or destination back to origin. And then in figure 2b, we actually can look at these ridges in terms of the outcomes of these origin points. So you go from many different origin points, in this case, evolving out to this ridge, which are the sort of, it's like a front in space. So you have this ridge that's described, and you get a sense of these ridges over time. So you have like the origin point, you have many different points in time. You're calculating out these ridges for each cell as it evolves, or family of cells as they evolve, and you end up with this ridge in space that describe sort of the endpoint or the consequence of these trajectories. So you can calculate the trajectory and you can calculate this ridge. And then the idea would be in cell migration, you would have an origin point in a series of ridges that would describe sort of wave fronts of migration. So the migration will follow this wave front outward. The second paper is from Royal Society Interface, and this is called Tissues as Networks of Cells, or its generative rules of complex organ development. So the abstract reads, network analysis is a well-known and powerful tool in molecular biology, so they're using network analysis to look at tissues. More recently, it has been introduced in developmental biology. Tissues can readily be translated into spatial networks, such as cells are represented by nodes and intracellular connections by edges. This discretization of cellular organization enables mathematical approaches rooted in network science to be applied towards the understanding of tissue structure and function. Here we describe how such tissue abstractions can enable the principles that underpin tissue formation and function to be uncovered. We provide an introduction into biologically relevant network measures and present an overview of different areas of developmental biology where these approaches have been applied. We then summarize the general developmental rules underpinning tissue topology generation. Finally, we discuss how generative models can help link the developmental rule back to the tissue topologies. So they're basically, what they want to do is derive these local developmental rules and how they can give rise to observed topological properties in multicellular systems. So they don't get into hypernetworks here, or hypergraphs, but they do give a good overview of this field, and especially in terms of how that relates to generative models.